Hello students, welcome back to my channel, and we are now dealing with Fourier series. In my previous video, I have explained to you what is Fourier series, for what they are used, etc. The introduction is given to you all. So today I am going to define what is Fourier series. So what is Fourier series? Any periodic function satisfying the Dirichlet's condition. I have discussed about this condition in my previous video. So any periodic function satisfying Dirichlet's condition can be expressed by an infinite series. So what is that infinite series? F of t is equal to a naught plus a1 cos omega t, a2 cos 2 omega t plus so on to an cos n omega t plus b1 sin omega t, b2 sin 2 omega t plus so on bn n sin n omega t. Now if you have seen here, we have one a naught value and all these remaining are the cosine terms and the other remaining terms are the sine terms. So I can also write f of t as a naught plus cosine term plus some sine term. Right? Now, apart from that, what else can I write this function as? See, if you can see here, we have a1, a2 and so on to an and cos omega t. So, when we have a1, we have 1 omega t, a2, 2 omega t and so on, an cos n omega t. Similarly, b1 sin 1 omega t, b2 sin 2 omega t and so on, bn sin n omega t. So I can write a naught is something which we have as a constant term. So I am writing a naught separately plus summation n equals to 1 to infinity an cos n omega t. So when I put n equal to 1, it becomes a1 cos omega t, 2 a2 cos 2 omega t and so on. Similarly plus bn sin n omega t. Right? So where I am defining a naught, an and bn, they are called as Fourier coefficients and they are defined as a naught is 1 by t integral 0 to t f of t dt, an is 2 by t 0 to t f of t cos n omega t dt, bn is 2 by t 0 to t f of t sin n omega t dt. An is a cosine term and bn is a sine term. Alright. Now apart from that, what else we can see from this infinite series? Now this a naught what we have, it is a Fourier coefficient which tells about the average value of the function of t. Okay, it tells about the average value of the function of t, and it also speaks about the area of one time period t. So in our previous video where we were discussing about Dirichlet's conditions, I have told you how we have found out the area of one time period. Right? That is nothing but 1 by t 0 to t f of t dt is itself telling us that it is the area of one time period t. Now, an, a1, a2 and so on and b1, b2 and so on, these are the coefficients of the sine terms and the cosine terms. Alright. Now, if an is greater than bn, that is the coefficient of cosine term is more than the coefficient of the sine term, then in the frequency signal, I have told you the Fourier series or Fourier transforms are used to study the frequency signal or to analyze the frequency signal. So there, if an is greater than bn, we have more of cosine values. Okay. And if an is less than bn, we have more sine values. That is, bn is greater than an. And what else can we see in these series is that this omega, we are calling it as fundamental frequency. I have told this in the previous video, but I am revising it again. Okay, so omega is the fundamental frequency. 1, 2, 3 and so on till n. We are calling them as harmonics. Right? This is the first harmonic, second harmonic, and so on, nth harmonic. So this is what we are analyzing from this Fourier series. Fourier series. Fourier series are used for analysis of periodic signals, as we already have seen the definition of this. Now, we are transforming these Fourier series so that we can use it to analyze the non-periodic signals, and that is why we are calling this as Fourier Transform. So what we are doing here is we are converting the time signals into the frequency signals. But there is a limitation here. So when we are converting the time signals to frequency signals in using Fourier transform, we are able to only convert the stable signals, right? So we are able to only convert stable signals. So to overcome this limitations, we are using Laplace transform, okay, which is a generalized transform. So this is transforming all types of signals. Now, why we have to transform or convert the time signals to frequency signals? Now, while we are studying chapter communication, we are using an important word called as the bandwidth. And bandwidth is frequency oriented. That is, bandwidth is nothing but higher frequency minus the lower frequency, right? So we are converting the time signals to frequency signals so that we will be able to calculate bandwidth in a much simpler manner. So that is why we are using the Fourier transforms as well as the Laplace transform. Now, what is Fourier transform? Fourier transform is, if f of x is periodic function of x, then the Fourier integral of f of x may be expressed as f of x is equals to 1 by 2 pi integral minus infinity to infinity e raised to I omega x into e raised to minus I omega t f of t dt d omega. So we have the time signal also, we have the frequency signal also. So what we are doing here is we are trying to convert it only into the frequency signal. So when we are trying to convert it, we will separate this t on one side and the omega on the other side. So we have 1 by 2 pi minus infinity to infinity e raised to I omega x d omega minus infinity to infinity f of t e raised to minus I omega t dt. Now, this can be written as 1 by root 2 pi minus infinity to infinity e raised to I omega x f of omega d omega. Now, this f of omega d omega is equal to 1 by root 2 pi f of t e raised to minus I omega t dt. Now, this 1 by root 2 pi into 1 by root 2 pi will give me 1 by 2 pi, and I have not changed the pattern of the expression. So, e raised to I omega x d omega is here only, and f of t e raised to minus I omega t dt is also in the same place. Now, this is called as the Fourier transform expression, and this expression where I have f of x is equals to 1 by root 2 pi e raised to I omega x f of omega d omega, this expression is an inverse Fourier transformation, right? So, one more thing what we notice here is, when we are talking about this Fourier transform, if you just see this particular part of this, it is representing, or it is looking similar to our Laplace transform. That is, how did we define our Laplace transform? 0 to infinity f of t e raised to minus st dt. So instead of minus s, I have minus I omega. So you can see they are almost same, right? So, but we have an extra term 1 by root 2 pi, and the integral is from 0 to infinity here, whereas the integral is from minus infinity to infinity in the Fourier transform. That is the only difference. Alright, let's move on to the next point. So the next point is infinite Fourier sine and cosine terms. So here we are trying to define them as separately as Fourier sine terms and Fourier cosine terms. So let's begin with the Fourier transform expression. So what is the Fourier transform expression? F of omega is equals to 1 by root 2 pi minus infinity to infinity f of t e raised to minus I omega t dt. Right? So this e raised to I omega t, from a mathematical background we can write it as cos omega t minus I sin omega t. So this, if I substitute in this expression, I am going to get it like this, that is 1 by root 2 pi minus infinity to infinity f of t cos omega t minus I sin omega t dt. Now I will separate these two integrals. So I will get 1 by root 2 pi f of t cos omega t dt minus 1 by root 2 pi minus infinity to infinity f of t I sin omega t dt. Alright. If the function is even, we know that f of t is equals to f of minus t. So f of minus t, when we are going to represent it in the integral, we see that this function is going to become equal to 0. That is minus infinity to infinity f of t I sin omega t dt is going to become equal to 0. And minus infinity to infinity f of t cos omega t dt, this is going to become twice the integral. It is going to become twice the integral. So therefore, when I substitute this in this part, I am going to get this complete part to be equal to 0, and this is going to be 2 times the integral. So 2 times the integral, I already have a root 2 pi here. So I will put this 2 by root 2 pi here. Now 2 by root 2 is nothing but root 2 by pi. So I can also write this as root 2 by pi. 0 to infinity f of t cos omega t dt. And for my simplicity's sake, I will just denote this as f subscript c of omega. So this is representing my Fourier cosine term. Fourier cosine term. So what is my Fourier cosine term? It is root of 2 by pi 0 to infinity f of t cos omega t dt. Similarly, if I take the function to be odd, I get f of t is equal to minus f of minus t. So when I substitute that, now the sine term will become twice and the cosine term will become equal to 0. But since I have an I here, I also get 2 by I here. So 2 by I 0 to infinity f of t I sin omega t dt. This I and this I will get cancelled. Okay. And the cosine term is going to become equal to 0. So again I get the similar type of expression as I got in the cosine term. Again this is going to be root 2 by pi. Root 2 by pi 0 to pi f of t sin omega t. And since this is a Fourier sine term, I can write this as f s of omega, s subscript. So this is denoting Fourier sine term. Now if I want to represent the inverse Fourier cosine term and inverse Fourier sine term, I have to just replace the f of t on the other side and f of omega I have to bring it inside. That is what we have to do when we are representing the inverse part. Okay, so f of t comes out and f of omega goes inside. So when we write that, we get f of t is equals to 2 by pi 0 to infinity fc of omega cos omega t. This is actually going to become d omega because we are converting it into frequencies. Right? F of t 2 by pi fc of omega cos omega t d omega. And inverse Fourier's sine transform, it is going to become 2 by pi 0 to infinity fs of omega sine omega t d omega. So therefore, I am defining the Fourier cosine term, Fourier sine term, inverse Fourier cosine term, inverse Fourier sine term. I have just abbreviated it so that it becomes a short term. Inverse Fourier cosine term, inverse Fourier sine term. So this is all about the definition and the way of expressing Fourier transform in different manners. I hope you have understood this, and in our next video we are going to discuss about the properties of Fourier transforms. So we have some properties of Fourier transforms. We will be discussing that in our next video. So hope you have understood and things are clear. If you have any doubts, please comment on the comment box, and if you like my video, please like it, subscribe it and share it. This is very important. Please share it to your friends so that they will be benefited too. Thank you. Hope you have a good day.